Hi class, today we're going to start section 10.2, which is on systems of linear equations in several variables. Okay, so first, a linear equation in variables is an equation that can be put in the form a1x1 plus a2x2 all the way to a(n)xn equals c, where a1 through an and c are real numbers and x1 through xn are variables. And then we keep using the term linear, so I want to really kind of give y'all an example between a linear equation versus a nonlinear equation. So a linear equation might look like 6x1 minus 3x2 plus the square root of 5x3 equals 10, or x plus y plus z equals 2w minus 1/2 versus x squared plus 3y minus the square root of z equals 5, or x1, x2 plus 6, x3 equals -6. So here on the linear side, our variables all stand alone with just a coefficient in front. They're not multiplied by anything, they're just as they are, and you can move them easily from the left to the right side of the equal signs. Versus over here, we have an x squared. So this makes it not linear. Actually, you know what? I'm gonna make these red to make them different. And then the second equation, we have an x1 times x2. So that makes them very difficult to separate or do anything with. Because we could just add or subtract on the left side. On the right side, we'd have to divide things out, which is it's a lot different when you're using a variable. All right, so we're going to look at solving a linear system. So the following are two examples of linear equations in 3 variables. The second system is in upper triangular form, also called just triangular form. That's what we'll often simplify it to, because we're never going to use lower triangular form in this class, but it's technically upper triangular. And you'll see why. So that is the variable x appears only in the top line and doesn't appear in the next two. Similarly, y appears in only the first two equations and not in the last. Okay, so what this means is, if we look at our first system, this is going to be x minus 2y minus z equals 1, a negative x plus 3y plus 3z equals 4, and a 2x minus 3y plus z equals 10, versus our second system, which will look like x minus 2y minus z equals 1, y plus 2z equals 5, and z equals 3. So this here, this is our triangular form. You can see how it kind of looks like a triangle. Okay, so we're going to look at this example here. Triangular systems using back substitution. So if we look at this system that we have, I'm going to rewrite it, so don't worry. We have an x minus 2y minus z equals 1, a y plus 2z equals 5, and a z equals 3. And you might notice that I like to put a line through my z's to differentiate them from my 2's. You don't have to do this, but it does sometimes help if you're getting confused between your 2's and z's. All right, and then we're going to call this one equation 1, this one equation 2, and this one equation 3. Actually, you know what? I meant to make these blue. There we go. Okay, so we can plug equation 3 into equation 2 to solve for y. So if we take our y plus 2, we plug in 3 for z, equals 5. This gives us y plus 6 equals 5, which gives us y equals negative 1. And now we can plug z equals 3 and y equals negative 1 into equation 1 so we can solve for x. So we have x minus 2 times negative 1 minus our z is 3 equals 1. Well, this is x plus 2 minus 3 equals 1. So x minus 1 equals 1. Therefore, x equals 2. So now we've solved our system. So the solution is x equals 2, y equals negative 1, x equals 3, or in that nice triple, we used ordered pairs last time. Now we're going to use an ordered triple. with our 2, -1, 3, where this is our X, Y, and Z placement. So to change a system of linear equations to an equivalent system, so an equivalent system means that it will yield the same solution as the original system. So to get one of these equivalent systems, we can use elimination. And what this means is, if we were to write out our operations that yield an equivalent system, okay, so operations that will yield an equivalent system. So the first one is we can add a non-zero, because just adding a 0 multiple is just adding 0. So we can add a non-zero multiple of one equation to another. So we could theoretically add like 5 times equation 1 to equation 2, and that will still give us a system that works. 2, we can multiply one equation by a non-zero constant. So like for an example, if we were to have 3x plus 6y plus 9z equals 3, if we divide or we multiply everything by 1/3, which is basically dividing by 3, this will become x plus 2 plus 3z equals 1. So this is a step that will maintain our solution, because we're scaling both the left and right-hand side of these equations by the same constant. And then 3, we can interchange the position of 2 equations. So for example, with this, if we were to look at our system up here, if we were to just switch equation 2 and 3, we could still take the solution we have as z equals 3 and plug it in. We didn't have to order this the way we did. It just is very helpful for solving. Okay, so to really show off what these operations do, we're going to solve a linear system. We use these above operations to change our system into the triangular form, and then solve with back substitution. And this process is called Gaussian elimination. right, so for example, we're going to solve the following system using Gaussian elimination. So our system is going to be x minus 2y plus 3z equals 1, x plus 2y minus z equals 13, and 3x plus 2y minus 5z equals 3. Where this is equation 1, equation 2, and equation 3. So first, let's eliminate the x from equation 2. So to do this, we're going to subtract the first row from the second, or the second row from the first. So that's going to be, if we have x minus 2y plus 3z and x plus 2y minus z equals 13, and we subtract this, we're going to get a 0x minus 4y plus 4z equals negative 12. All right, and now I'm just going to do a nice quick step, and we're going to divide the negative 4 out, which is the same as multiplying by negative 1/4, just because I see that this will yield a slightly cleaner equation. Okay, so now we need to rewrite our system with our new equation 2. So we're going to have x minus 2y plus 3z equals 1, and then our y minus z equals 3, and then we didn't do anything to equation 3, so right now it stays the same. Okay, so now we're going to eliminate the 3x in equation 3. And to do that, we're going to multiply the first row by x minus 2y, 3z equals 1. We're going to multiply it by negative 3, and then we're going to have our 3x plus 2y minus 5z equals 3. And this becomes negative 3x plus 6y minus 9z equals negative 3. 3x plus 2y minus 5z equals 3. And when we add these together, we end up with a 0x plus 8y minus 14z equals 0. And on this one, we're just going to leave it the same because 8 and 14 don't simplify too easy. We could theoretically factor out a 2, but it's not super necessary for this next step. So we're going to rewrite our system with our x minus 2y plus 3z equals 1, our y minus z equals 3, and our 8y minus 14z equals 0. All right, so from here, now we need to get rid of the y in equation 3. Okay, so to do this, it's going to be very similar. We're going to multiply the second row by negative 8. And then we're going to, that will give us a negative 8y plus 8z minus 24. And then we're going to write our third row, 8y minus 14z equals 0. and we're going to add them together. That's going to give us a 0, y, and then 8. That should give us a negative 6z equals negative 24. Okay, and then here, if we multiply by negative 1/6, that will give us a z equals 4. So now we can write our triangular system, which is x minus 2y plus 3z equals 1, a y minus z equals 3, and our z equals 4. So this is now our upper triangular system. So with back solving, we get, so we'll plug our z equals 4 into the second equation. We have y minus 4 equals 3, which gives us, if we add 4 to both sides, y equals 7. And now if we plug in z equals 4 and y equals 7 to the first equation, we get x minus 2 times 7 plus 3 times 4 equals 1. So this is x minus 14 plus 12 equals 1. X minus 2 equals 1, so x equals 3. So this means that our solution is 3, 7, 4. All right. So this video I think is going to end up being too long. After giving y'all a really long 10.1 video, I'm going to stop the video here. So this is actually going to just be a part 1 video, and I'll do part 2 later. All right. Thanks, class. Bye.